Next, let's see another spatial equations. This spatial equation is called Euler Equations. Okay, if you have this form, a and b again are constants, or you have another form x squared y double prime times the constant times x y prime plus a constant times y equals 0. These two, if you see these two forms, it is called Euler equations. And for these Euler equations, definitely we have a method to solve, to find the solution. Okay, and then if you see in this format, then we need a changing variable. So the change of variables, because you can see that even though this is constant, but I still have the variables here. So I want to get rid of this variables, because so far we just learned that if I have a constant coefficient differential equation, my answers are one of these three types. So we try to make this equation to our constant coefficient differential equation. So we need to change the variable. So for change the variable, when we do change of the variables, that means we can get a constant coefficient second order linear differential equation. Constant coefficient second order linear differential equation. So how do I change the variable? So for Euler equations, we say that t equals natural log of x, which means x is e to the t, and then dt is 1 over x dx. Okay, so we will change the function of x into function of t to have a capital Y of t function. That means y of the lowercase y of e to the t, and that is y of x. Now we need to find y prime and y double prime, and we will use the capital Y to express y double prime and y prime. So first, y prime. What is y prime? Y prime means dy of x dx. Right? And this, we use the chain rule. Well, this is also equal to d capital Y of t over dx. Okay. And then doing the chain rule. So dy over dt, here dx, then we have dt and dt. So this case I have y capital Y prime times 1 over x. That means xy prime of x is capital Y prime of t. And then you can see that for xy prime, I can change this part to y prime of t. Then I keep the constant and eliminate the variables x. Now, let's see y double prime. So y double prime is dy prime over dx. And we just found the y prime here. That is the capital Y prime 1 over x dx. Okay, and here we have a chain rule. First, we'll take the derivative of our first term and keep the second term. And then keep the first term, take the derivative of the second term, which will be 1 minus 1 over x squared. Okay, and here we do the same thing, chain rule, but here we have y prime. Okay, do the chain rule. This is 1 over x dy prime over dx. But for chain rule, we have dt and also dt in the numerator. Then keep the second term, 1 over x squared y prime of t. Let's rearrange of this y double prime. We have 1 over x squared and y double prime of t minus y prime of t. Which means x y double prime, or x squared y double, or x squared y double prime is y double prime minus y prime. Now let's see. So x squared y double prime, I can substitute y double prime minus y prime, and xy prime will be y prime. So now let's change that, and we get y double prime minus plus a minus 1 y prime plus by equals 0. Okay, so now you can see that for this new equation, this is constant coefficient, right? Constant coefficient, linear second order differential equation. And then the solution will be either exponential, two different exponentials, or exponential and the other one is x times the same exponential, or the exponential times cosine and exponential times sine, right? So this is constant coefficient linear second order differential equation. And when you find the capital Y, that solution, that is capital Y, right? But originally, y of x is our solution. So the general solution, you need to convert it back to the lowercase y. The general solution y of t. Because you get y capital of t, right? And then we need y of t. That is capital Y natural log over x. Any questions for this? Well, that is the derivation, and that tells you that for this Euler equations, we have a change variables, and then we can find a solution easily. So you only need to know that for the Euler equations, t equals natural log x, and then you transform all x to t, and then you can find a solution. You don't need to really memorize this one, okay, or even this equation. But if you do more practice, then you know that if you see this format, then you can convert it to a minus 1 right away, and here's b. So let's see several examples. First one, we see that x squared double prime, y double prime, and x times y prime. And also here we have constant coefficients. So it is Euler equations. So we can get we just do changing variables. T equals natural log of x. And you will get y double prime, capital Y, okay, plus y prime minus 6y equals 0. To find a solution, this characteristic function is lambda squared plus lambda minus 6 equals 0. So your lambda could be minus 3 and also 2. That's two real distinct roots. So my solution, y of t, is c1 e to the minus 3t plus c2 e to the 2t. Okay, because lambda is either minus 3 or 2. But this is capital Y and the variable is t. So I need to change that to the lowercase y and also the x. So y of x is c1 e to the minus 3, and t is natural log x. So natural log of x plus c2 e to the 2 natural log of x. Then you get c1 x minus x to the minus 3 plus c2 x squared for x is greater than 0. All right. Next example. Again, we have x squared y double prime and x times y prime. And those coefficients are constant. So this is Euler equations. Then t equals natural log of x. You get capital Y double prime minus 6y prime plus 9 equals 0. And you have lambda squared minus 6 lambda plus 9 equals 0. Your lambda is repeated 3 and your lambda is 3 and repeated 3. So your solution y of t, that's c1 e to the 3t, since you have repeated roots, so the second solution is c2 here. We have t times your exponential. And we have already checked that these two solutions are linear independent. Okay, so they can form a fundamental set of the solutions. Then back to the y of x, you get c1 x cubed plus c2 x cubed natural log of x. All right. If you don't have any questions, let's see next example. This is apparently Euler equations, and then we can change that to capital Y. We get capital Y double prime here minus 6y prime plus 10y equals 0. And you will see this is lambda squared minus 6 lambda plus 10 equals 0. And you get your lambda is complex numbers, 3 plus I or 3 minus I. Then your y, the solution will be C1 e to the pt. Okay, here p is 3. This is p and q. So here, why we don't have e to the px? Because here is 0 plus 3i. Okay, so e to the 0x is 1. Okay. So here we have e to the 3t and the cosine natural log of x, and also c2 e to the 3t sine. Oh, we have t. Here we have t. And then your y of x is c1 x cubed cosine natural log of x, and c2 x cubed sine natural log of x. Okay. Questions for the Euler equations. You can practice that. I give you like 4 more exercises. Okay. Next. So far, we just have the homogeneous equation. Okay. The forcing function is 0. Now, if it is not 0, this is non-homogeneous. If it is non-homogeneous, we know that the solution should be the homogeneous solution plus the particular solution. Okay, but how do we find the particular solution? So it depends on this f of x. And we call this is a method of undetermined coefficient. This coefficient is talking about the coefficient in f of x. So here's in f of x. Okay, and this forcing function will give an idea of your particular solution. Okay, what does that mean? For example, according to this f of x, we can guess the particular solution. Suppose the f of x in this example is polynomials. Then what is your particular solution? Since it is polynomial, write it down, polynomial. then my solution, my particular solution should be polynomial, right? Because if you take the derivative, the polynomials are still polynomials. You cannot guess that, okay, since it is polynomial, then my solution, the particular solution is, for example, sine square. If you have a sine, or sinusoidal waves, or cosine, when you bring this back, they won't satisfy this equation, because here you always have a cosine or sine, but this you have polynomials, so they couldn't be equal. So since the f of x is polynomial, then you guess the particular solution is also polynomial, because the polynomial is ax squared plus bx plus c. You take the first derivative, you get 2ax plus b. And you take the second derivative, you get 2a. And then you bring this back, then they can compare the coefficients. Okay. So we can try the particular solution is polynomials. And of course that the order cannot exceed the order of your differential equation. You cannot guess that, okay, this solution should be like times x to the 5 plus bx to the 4th. Because here, when you take the first derivative, you get 5ax to the 4th, right? And the second, you get 20ax cubed. But on the right-hand side, I don't have x to the 4th or x cubed. Then I cannot compare those coefficients, so they won't satisfy. Unless you have the same order, you may have chance. Okay. And here's the note that the derivatives of the polynomials are still polynomials. So it could be the particular solution. And the degree, in this case, should be less than 3, because the order of the forcing function here is 2. You take derivatives, you cannot have the order greater than 2. Okay. So suppose if you have x to the 5, then y prime is 5 times x to the 4th. Y double prime is 20x cubed. And you see that those order, the degree, is greater than 2. Then I cannot compare. I cannot bring this back to my original equation, because there's no x to the 5 or x to the 4th or x to the x cubed. Okay. So now in this case, let's see. Suppose we guess the particular solution is polynomials in degree 2 or the order 2. Then we need to bring this particular solution back to this equation. It should satisfy. Therefore, we can find the constant a, b, c. So y prime, we have 2ax plus b. And y double prime, we get 2a. So therefore, we bring this to this original equation, we get 2a minus 4, and your y is ax squared plus bx plus c. That should be equal to 8x squared minus 2x. Then you can compare the coefficients. So first, let's rearrange that. For x squared term, we have minus 4a minus 8. For x term, we have minus 4b plus 2. And the rest is 2a minus 4c. It should be 0. So minus 4a minus 8, and it should be equal to 0. Minus 4b plus 2 should be 0. And 2a minus 4c should be 0. Then you get a equals minus 2. B is 1/2. C is minus 1. Then your particular solution is ax minus ax squared, minus 2x squared plus bx 1/2 of x times x minus 1. Remember that this is the particular solution. Our general solution should be the homogeneous solution plus the particular solution. Then what is the homogeneous solution? Now, we need to consider y double prime minus 4y equals 0. This equation, homogeneous equation, has the general solution y of h has general solution y of h, and since it is constant coefficient equation, so we have this one. I have two different roots. So C1 e to the 2x, and the other one is C2 times e to the minus 2x. I think, yeah. So finally your general solution y is the homogeneous solution plus the particular solution. Any questions? Here, let's see the example. If the forcing function, it is non-homogeneous, obviously this is non-homogeneous equation. If the forcing function is exponential, then our particular solution should be also related to the exponential. So here is a note. We cannot say that my particular solution is sine or cosine, because when I take the derivative, they won't become the exponential, or even polynomials. Because when I take the derivative, I cannot change these polynomials to exponential. So only exponential, the particular solution is exponential, that may satisfy this forcing function. So here's the note. We need to observe this e to the 2x, this exponential. The derivative of the exponential is exponential. The derivative of e to the 2x is 2 times e to the 2x. Therefore, I can guess my particular solution is a constant times e to the 2x. You cannot say that it should be the e to the 4x or e to the 6x, because if you take the derivative, the form is still e to the 4x. It's not 2x. So I cannot compare the coefficients and to find the coefficient a, or the constant a. So in this case, a times e to the 2x, bring this back to the original equation. We have 4a e to the 2x plus 4a e to the 2x minus 3a e to the 2x. That should be equal to 4 times e to the 2x. And you'll get the a is 4 over 5. Then your particular solution is 4 over 5 exponential to the 2x. We also need to find a homogeneous solution, which is given by the homogeneous equation. Okay, set the forcing function 0 to be 0. Then you get the homogeneous solution C1 e to the minus 3x and C2 times e to the x, since the roots of the characteristic equation is two different distinct real roots. So the general solution is y includes the homogeneous solution and particular solution. Next, if the forcing function is sine or cosine functions, then definitely we will guess my particular solution is a sine function or cosine function, or even the combination of sine and cosine, because if I have a sine function, I take the derivative is cosine, and I take the second derivative, it becomes minus sine. So actually I should have the combination of sine and cosine. So we try, here we try our particular solution is constant c times sine. And also I need the same frequency, always 2x, because sine 3x, sine 5x, they are not the same, and I cannot compare, and they won't satisfy this equation definitely. So here I have 2x, and then d cosine 2x. So y prime, you will get 2c cosine 2x here minus 2d sine 2x. And then y double prime, you have minus 4c cosine 2x, sine 2x. Here minus 4d cosine 2x. So bring this back to the original equation. Then rearrange that. We have 2c plus 10d plus 3 times sine 2x. That should be equal to minus 2d plus 10c times cosine 2x. Just bring this back to the original differential equation, then you get here. Okay. And we know that cosine and sine, these two functions are linear independent. So the only way that I have an equal sign here, that means the coefficient should be 0. So since sine and cosine, sine 2x and cosine 2x are linear independent for all x, then 2c plus 10d plus 3 is 0. And then minus 2d plus 10c should be 0. You get c minus 3 over 52 and d minus 15 over 52. And don't forget that we need the what? The homogeneous solution. So also y prime minus, what is that? 5y prime plus 6y is 0. Then the homogeneous solution is c1 e to the 3x and also c2 e to the 2x. There are two distinct real roots, so I have two different exponentials. Then the general solution, let me write down here. The general solution is includes the homogeneous solution and particular solution. Next example, well, we have exponential again. Okay, so we try the particular solution is a times e to the x. But however, when you bring this particular solution back to the differential equation, we get 0 equals a times e to the x. Because remember that for these differential equations, we have we should have a fundamental set of solutions. And then e to the x is a solution already for the homogeneous solution, a homogeneous equation. So this is a solution of y double prime plus 2y prime minus 3y equals 0. So no wonder that you cannot guess e to the x again, because this e to the x is in the homogeneous solution. So in this case, we will try another one. We can try still need to have the form of e to the x, because every time when you take the derivative, they can satisfy this forcing term. So here we still have a, but we add more, like x, we add one term, x times e to the x. And then y prime is a times e to the x, and also plus a times x times e to the x. And y double prime, that is 2 times a to the e to the x plus a times x e to the x. Then you can find 4a equals 8, then a equals 2. Then that is your particular solution. Plus your homogeneous solution, then that forms the general solution. Okay. Another case is here, I have exponential as our forcing function. So we guess my particular solution is also e to the 3x and times a constant. But again, e to the 3x actually is the solution of the homogeneous equation. So notice e to the 3x is a solution of y double prime minus 6y prime plus 9y equals 0. Same situation as the previous example. Then we guess a times x times e to the 3x. But if you guess a times x times e to the 3x, it is also the solution. X e to the 3x is also a solution, since they have repeated roots of y double prime minus 6y prime plus 9y equals 0. Because the characteristic function we get the repeated root. So lambda equals 3 is repeated. That's why e to the 3x is a solution. X times e to the 3x is also a solution. Then what should we do? Don't worry, that we can try. We still have the form of e to the 3x, but this time we can have x squared rather than x times the e to the 3x. And you will get a equals 5/2. Okay, and then during your free time, you can do it by yourself or do them with your teammates. The last form we are going to talk about is the method of variation of parameters. So in the past, we consider that all the p and q function of x are constant. They have constant coefficient of the equation. But what if they are not constant? If they are not constant, then here we have a particular solution, say the function of x times y1 and the function of v times y2. And then u and v, these two functions over x, will form a particular solution. So suppose my particular solution is this form. The first derivative, okay, using the chain rule, take the first term, keep the first term, take the derivative of your second term. And take the derivative of your first term, keep the second term. And then for the v times y2 here. And the y double prime, then bring y prime and y double prime to your original differential equation. You'll get a bunch of terms here, and you can rearrange that. Okay, you should do that by yourself and rearrange that, okay? When you rearrange that, you put everything related to u together, everything related to v together, and you can see that this y1 and y2 are the solutions already for the homogeneous differential equation. So here, this should be 0. And this term also should be 0. Okay. And let's see the rest terms. Okay. I can combine some terms to get, well, this one is the same, okay? And we can combine y prime u prime and also u double prime y1 be here. And I keep one outside. And the second here. Okay, so maybe I can use this term plus this is here and here. And how about the green one? All right. So I combine these two, P and the rest here. Okay. So finally, we get another differential equation. And we need, this should be f of x. And the derivative terms should be 0. So y1 u prime plus y2 v prime is 0. And also y1 prime u prime plus y2 prime v prime equals 0. Not 0. The forcing term f of x. Okay, seems you can see that this is the same. I said 0. That'll be easier if this is 0 and the rest term is the forcing function. Then that will satisfy this equation. Okay. For this two, to get the solution of u prime and v prime, we can use this determinant to find the solution. Okay, so the numerator, for the first column, you use the right hand side coefficients 0 and f of x. And the second column, you get the coefficient from v prime. And the denominator, we put y1, y2, and y1 prime, y2 prime. So if you want to get u, the first term, the solution, u prime, the solution, you just replace y1 and y1 prime to 0 and f of x. And the denominator here is remember the Foucault-Skyne test? This is the w. And the v prime, again, I think I can probably just copy and paste. Same. And the numerator, well, since it's v prime, so I keep the first column, y1 prime, and the second one will be 0 and f of x. We will also learn this method when we talk about the linear algebra. Okay. So the u will be minus y2 f of x divided by w of x dx. And your v is y1 f of x w of x when we use this method. Here's the note: the coefficient of the y double prime should be 1. The coefficient of y double prime is 1. Okay, now let's see this example. We know that we can use the Euler function to find Euler equation to find the homogeneous solutions. Here are the two linear independent solution. y1 is x. y2 is x to the fourth. Now I need to use these two to find the particular solution. Okay, so u of x y1 and v of y2. And your forcing function f is x squared plus 1. And since your y1 and y2 is here, the w function, the Hornstein test here, this is x1 x cubed x to the fourth and 4 times x cubed. This gives you 3 times x to the fourth, not 0. So again, they are linear independent. So you can take the same procedure. Okay, you please do that at least one time by yourself. Follow those steps till here. Okay, till here you can easily see these two equations. Then u of x that be minus integration x to the fourth times the f of x divided by 3x to the fourth. This gives you okay, and also the Vx. If you are stuck in the middle of the process, just let the TA or me know. Okay, you can figure out how do we do this. Okay, here I give you the final answer. So the particular solution is u times y1 plus v times y2. And remember that this is just the particular solution, not the general solution. So the general solution is the homogeneous solution plus the particular solution. Okay, next, the higher order. So far, we just mentioned about the first order differential equation and also the second order differential equation. Here, this is the nth order linear homogeneous differential equation. So you see that the forcing term is 0. Okay, and this is the nth order. Since we have nth order, then we may have R solutions from y1 to yr. And since they are solutions, the linear combination of these solutions is also a solution. Okay, well, then we can use the same method as we learned. And if we have a constant coefficient, then we can also guess that our solution is e to the exponential e to the lambda x. For example, if we have a third order differential equation and these coefficients are constant, then we consider the solution is exponential as well. Then the characteristic equation is lambda cubed plus 5 lambda squared plus 3 lambda minus 9 equals 0. You can find the root. The roots are 1, minus 3, minus 3. Two repeated roots. Then we can guess that the y1 should be e to the x, y2 e to the minus 3x. I have a repeated roots, so the third one should be x times e to the 3x, minus 3x. We can also check those three solutions are linear independent or not. So here we have e to the x, and take the derivative e to the x, take the derivative again e to the x. y2, this is y1, okay, y1 prime, y1 double prime, y2 e to the minus 3x, take the derivative minus 3 times e to the minus 3x, and then 9 times e to the minus 3x. So here's y2 prime, y2 double prime, y3 x times e to the minus 3x. When you take the derivative, e to the minus 3x minus 3x times e to the minus 3x. Take the derivative again. Here is your final answer. Okay, this is y3 prime, and y3 double prime. Okay, if I take the determinant, that is 3 by 3, it's 16 times e to the minus 5x. And this is not 0, so actually those three solutions are linear independent. The general solution will be c1 e to the x plus c2 and c3. I need additional x here times e to the minus 3x. If we have a multiple, the real root of lambda for a multiple of k in the characteristic equation, then how do we guess our solution? If lambda is a real root of multiple k of the characteristic equation, then the solution is, so every time you just times x times x times x. The first is e to the lambda x. Then the second one will be since it is repeated. So x times e to the lambda x. Next should be x squared times e to the lambda x. And so on till the multiple of k. So this should be x to the k minus 1 e to the lambda x. And you will check that they are linearly independent. Okay, and that is our content for the first part, ordinary differential equation.